In this video, I'll show you how to solve the ALEKS problem called drawing the MO energy diagram for a period 2 homodiatom. So I think when I'm asked to draw a molecular orbital diagram, I think that it is easier for me to start by drawing the atomic orbital energy diagram. So that's what I'm going to do first. For my fluorine, I'm gonna start by just drawing the electron diagram, the box diagram, whatever you want to call it, for the single fluorine atom. Now, as you know, this is based on the electron configuration for fluorine, or the number of valence electrons for fluorine, however you want to think about it. If we kind of zoom in here, we can see that fluorine is located right there. It has a total of 9 valence electrons. Its electron configuration is going to be 1s2, 2s2, 2p5, and we're going to reflect that over here with a box diagram. So there's my 1s. I said it was 1s2, and my 2s I'm going to put up here. There's my 2s orbital, 2 electrons in there as well, and then my 2p orbitals way up here, my 3 2p orbitals that have a total of 5 electrons in them. I made those boxes way too small. 1, 2, 3 2p orbitals with 1, 2, 3, 4, 5 electrons, 2, 4, 6, 8, 9 total electrons for fluorine. Now again, this is the atomic electron diagram, or the atomic orbitals for the single fluorine atom. In the F2 molecule, basically we're going to take 2 of these atomic diagrams and we're going to combine them together to make the molecular diagram. So what I'm going to do, I'm going to erase my little energy axis there. I'm going to scoot this over like that, and I'm going to copy it and paste it. So now I have 2, and these are my 2 fluorine atoms in the F2 molecule. And as I said, these are going to come together to make the F2 molecule, which I'm going to do in a different color. So for starting with our 1s, for the electrons in the 1s orbital, the 2 individual 1s orbitals are going to come together, and they are going to make a bonding sigma orbital and an anti-bonding sigma orbital. The bonding orbital is going to be lower in energy. The anti-bonding is going to be higher in energy. This is going to be, both of these are sigma orbitals. The higher energy one is a sigma star, an anti-bonding orbital, and these are going to get the subscript 1s because these sigma orbitals are coming from 1s atomic orbitals. There are a total of 4 electrons in the respective 1s orbitals, which means that there are going to be a total of 4 electrons in these sigma 1s orbitals, sigma 1s and sigma star 1s. We're going to do the same thing for our 2s orbitals. The 2s orbitals are going to combine together to make a sigma and a sigma star. So there's our sigma 2s and our sigma star 2s. 2s because they're coming from the 2s orbitals. Lower energy is sigma, higher energy is sigma star, bonding versus anti-bonding. A total of 4 electrons, 1, 2, 3, 4. Now when we get up to the 2p orbitals, things get a little bit trickier to predict. In general, we are going to be making a sigma orbital and 2 pi orbitals, and then we're going to have the respective anti-bonding as well. So we're going to have 2 pi stars and a sigma star as well, coming from these 2p orbitals. However, the relative organization, the relative layout of the pi and the sigma star and the pi star, this relative layout is going to depend on which element we're actually dealing with from the periodic table. So the cutoff line is between 5a and 6a on the periodic table. If you are dealing with an element in 5a or less, which we are, wait, no, we're not. We're dealing with fluorine. If you're dealing with an element in group 5a or lower, then you are going to have an order of pi, sigma, pi star, sigma star. And that may not make a ton of sense right now, but it's going to make sense when we put these orbitals together. If you're dealing with 6a or higher, your order is sigma, pi, pi star, sigma star. So before you put these orbitals in place, you need to pay attention to where your atoms are located. Ours are on this side of the line, which means that my organization of the molecular orbitals coming from 2p is going to follow this pattern. I'm going to have a sigma orbital down here. This is going to be a bonding orbital, sigma, and it is coming from the 2p's. So this is going to be sigma 2p. And then above that, I'm going to have my pi orbitals. There are 2 pi orbitals, pi bonding orbitals. Pi also comes from 2p. And then above that, I have my pi stars. There are 2 pi orbitals. This is pi star, anti-bonding, also 2p. And then above that, I have my sigma star, also comes from 2p. I have in my 2p orbitals a total of 2, 4, 5, 6, 7, 8, 9, 10 electrons, and I'm going to fill those in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm filling them in using Hund's rule, using the same type of principles that we use when we're filling in atomic orbitals, meaning that we're starting on the bottom, working our way up, making sure that every orbital gets 1 before any gets 2, etc. So this right here is the molecular orbital diagram for the F2 molecule, and this is what you will put in for your answer. So you won't be putting these in. This is just kind of a tool to help you come up with the molecular orbital diagram. Now, I do want to come back to this concept here. If we had been dealing with, like, let's say nitrogen instead of fluorine, so if we'd been dealing with nitrogen, when it was time to fill in this portion of the energy diagram, we would have needed to reverse the positions of these orbitals right here. So it would have looked like this. It wouldn't have looked exactly like this because the number of electrons would be different, but in terms of the order of the orbitals, this is how we would have laid that out.